Hello, folks. So today we're going to speak about horizontal scaling of a Web3 system to the sky and beyond. That's a nice and humble way to get started. One key sentence, all you need to success is love. Now remember this thing because we're gonna come into that later on this stage, and you will see what I meant. But it's actually a nice truth here that we found. First of all, let me introduce myself. I am Paolo. I'm a staff node core member and developer experience team at Nearform. You can find me on Twitter and on GitHub on those handles. And that teeny little dot is that where I come from the southern Italy, middle of nowhere, one of the regions that they pretend, the rest of Italy pretend we don't exist. They just not acknowledge our existence, which is worse for them. They're losing a lot of beauty, but that's their choice. Now, first of all, how many of you are familiar with IPFS in Web3 in general? Okay, I will start very slow then. The IPFS is Interplanetary File System, so that's a very humble naming for a protocol, and was basically a protocol designed with the intention to preserve and grow humanity knowledge forever in a way that is upgradable and resilient and more open. And when I say open, I mean that it's public. It's not really open because they are very technical protocols, but they claim to be open. In order to make really accessible for non-technical people, and if you allow me, also technical people, because sometimes it's very hard to grasp these technologies, services like Web3.storage have been created in order to make storing files on IPFS way easier, even for non-technical user. At the end of the day, Web3 storage is a web UI you can use to upload your files and consistently get retrieve them back, or an API you can use for the same purpose, but it's way easier than to set up your own IPFS node locally using the Go implementation, JavaScript implementation, and so forth. Before I can proceed, I have to introduce just two main concepts. I promise there are the only two main concepts I will introduce today in order to let you understand how IPFS works. The first one is the concept of content identifier, for short CID, which in the future I will also refer as block. The block is the data associated to a CID, but I will use the two terms interchangeably. Now, the CID uniquely identifies a chunk of data in IPFS. Now, it also implicitly includes the information to verify if the data has been tampered or not, because the CID is also the cryptographic hash of the content. So when you have a CID, you ask for a CID and receive the data, you can recompute the hash and eventually get the same CID back. Otherwise, you have got something else. CIDs are gathered in a content archive format, CAR format for sure, which is basically a concatenation of basically CID block, plus an additional header. Now, since this format uses integer prefix format for storing, is very easy to parse and is well suited for streaming parsing techniques. Remember this concept because it's going to come back in a bit. Now, as you know, I work for Nearform, so the question was, what was wrong? Why our client reached out to us and say, can you help us? Well, these people have what, as a developer, I call the best problem that a company might actually experience, which is they're not able to handle their growth anymore, which means that they're being very successful in their business, but unfortunately there are technical challenges on being so successful, especially when it comes all of a sudden. For all the DevOps people here, you know what I'm talking about, when you all of a sudden have to double the size of your machines or scaling network, I mean all the things that you can imagine. Now, the original Web3 storage implementation were struggling to handle their daily rate. And when I say their daily rate, I'm talking about millions of uploads per day. Literally million on a steady, it's not a burst, it was a steady rate of millions of uploads per day. The problem is that the original implementation was simply saying, I actually spin up a new IPFS node on the network, and I wait for that node to be effectively added to the network and be used by the rest of the network. The problem is that, for a reason that I will explain you in a bit, adding a node to this network was taking literally 48 hours in order to basically add a new node available for resolving, serving, and retrieving the data. That was the problem. And then it came the question. How can we use AWS services to make the service horizontally scalable with no limits? Now, the things that at Nearform we get the best client, which usually have the simplest question possible, like, can you give me the sun? Pretty much, because you do want to scale without no limit, that's it. There are no constraints, nothing, whatever. That was the challenge. So we settled, when we started analyzing the architecture, we set few goals that we need to achieve in order to be successful in this project. First of all, obviously, we need to handle the growth. So once again, we have to handle millions of uploads per day. Second, that's something we established because we immediately noticed that that was the only possible way to go. We need to be stateless. All the services that we have, they can have a shared database somewhere, but the host itself must be stateless at any stage, so they can go up and down at any time. Finally, use the cloud, because that's the only way you can reliably add and remove machines at any time, because if you go on-premise, it's going to be hard, because you technically must have physical machine that you can plug in, plug out, restart, maintain, and so forth. Then it comes the solution. Hello, I'm Elastic IPFS. Elastic IPFS, that's for short I will call EIPFS, and as an Italian speaker is a mess to pronounce this acronym to me, so I'm sorry for that, is an architecture that we designed that was divided the problem in 3 different subsystems, which I will show you in a bit. And the architecture was designed with global replication in mind. So even though we currently have all a single deployment, nothing is prohibiting another deployment to be made on the same region, on another cloud, and so forth. Moreover, new nodes could be added and removed at any time on the network without any penalty. You can find on GitHub all the specification there, because the entire architecture is public, as basically IPFS people always have work on public repository. This is the short graph that I don't expect you to read, so it was just for making fancy slide. But if you go on the GitHub URL over there, you will find that diagram and you can take a look. Now, one thing that I want to make very clear immediately foremost. As most people realize, Web3 is a decentralized attempt initiative that is meant to be to have the world in a decentralized way, more resilient, open, and not close to very big players in the field, basically. Now, you have to start from somewhere. So we started on AWS, but we have no vendor lock-in. The AWS implementation is just the first implementation which can be seen as the reference implementation. In the IPFS world, there is similar stuff with the client implementation, because there is the Go implementation and the JavaScript implementation. Nobody at Protocol Labs or other big players in the field are actually saying you should use Go or JavaScript. You can implement your own. We just provide you the reference one. So AWS was the reference implementation for EIPFS, but, and you will see in a bit, we're only using generic components. Basically, all you need in order to have EIPFS is an object storage system, a queuing system, and a serverless system. And Kubernetes is completely fine or something like that for the job. If you have all these components, you can deploy Elastic IPFS anywhere. in theory, pushing really to the edge, if you have just a node machine and a Redis machine, or on the same machine in theory, you can have elastic IPFS. You just have to adapt some code, but that's the minimum stuff. That's absolutely fine. Now, what is your limit? The DevOps. Be gentle with your DevOps, because they have to manage all the reliability, so you can do horrible stuff with this architecture if you set up very wrong, so be gentle with them, please, on their behalf. Now, let's talk about which kind of data we are storing in elastic IPFS. We're mostly storing 3 tables in DynamoDB. The first one is the cars table item, which contains generic information about the indexing car system, including the full path on S3. Because basically, the way it works is that Web3 storage people upload a car file on S3, and then using the AWS triggers, we start a processing pipeline. Now, the data is stored on Dynamo. The cars table is pretty simple and is mostly used to track the control of the queue and see when thing went wrong, what is the status of a car file, and so forth. Then there is the blocks table, which basically just stores the multi-hash of the block, which is the same, or the CID. There is a subtle difference that you don't care about at the moment, but you can consider part of the CID. The created that and the type of the block that we have indexed. This table is mostly used for debugging. And then there is this table, which is the most important table. That's the block position item table. So basically, it's a table that says, look, I got this block that has this multi-hash. I got in this car file the full S3, the path of the car file. And this is the length, and this is the offset where you can find the block in the car file. Because as you remember, I told you that the car file is meant to be a stream of and concatenation of blocks. So if you want to retrieve a block from a car file, you just need to know the length and the offset, and in theory, you can do random access. You don't have to sequentially read the entire car file, which is a very important property, considering that many times car files are big in the order of the terabytes. So in order to sequentially read the terabytes, it will take you ages. And here it comes. These are all the core concepts you need to understand how elastic IPFS works. Now it comes to the first subsystem of the elastic IPFS, which is the indexing subsystem. Once again, this is the graph for sure. Don't get blind trying to read it. You can find it online later. But that's the flow, which I already partially described. The car file from Web3 storage is copied to S3 bucket. The S3 bucket is configured to create an event on an SQS topic. The SQS topic is linked to a lambda, the indexer lambda. The indexer lambda is very easy. It will basically sequentially read and analyze the car file, and for each block, it will store the data on the tables that I just showed you before. Very simple. Then, for each block, it will just write the multi-hash of the block on a second SQS topic, which is called the publishing SQS topic, which are basically used to trigger the second system of the elastic IPFS, which is the publishing subsystem that I will introduce in a bit. One very, very interesting information about the indexing lambda is that initially the lambda was created as an idempotent lambda. Are you familiar with the concept of idempotence? For people that don't know what the term means, is basically that if you execute the same function with the same input at any given time, you will get the same output without any side effect. So you can execute this function to the infinite, basically. Now, initially, we designed the indexing lambda to be idempotent because our fear was that since you can receive very gigantic car files, and consider that in IPFS, the number of blocks in the car file is not linearly correlated to the number of blocks, unfortunately. It's completely unrelated. which means that you can have a car file that is 100 megabyte big and contains literally millions of blocks. And you can have a car file which is 1 terabyte in size and only contains a single block. They are completely unrelated. Our fear was that if you have a car file which has a lot of blocks, writing those blocks to Dynamo might time out the Lambda. Or if there is an error and you have to restart from scratch, you have to do the same operation over and over again on a gigantic number of blocks, basically, right? Now, fun fact is that in order to track idempotence, we have to read and write the state continuously from Dynamo. And believe it or not, Dynamo told us to slow down because we were hammering Dynamo. We were too fast, and Dynamo said, I cannot handle your load. And they start shutting us down, giving a 500 error, which is unbelievable. So we searched for an alternative, and we made the simple rule. Okay, let's remove idempotence, just go in write-only mode, so we can also batch the writes and see what happens, right? Well, what happened was that we were able to be really, really fast, and surprisingly, our failure rate was close to 0. So idempotence was an unneeded overhead, and if you pass me term over-engineering, that was completely unneeded, and we completely discard them. Disclaimer, I'm not blaming anyone because I was the one who wrote the idempotence in the first way, and then all of a sudden it was removed by my colleagues, so kudos to them because they made the very right choice. Now, we have to talk about the DHT, because the DHT has been the most challenging part of Elastic IPFS. The DHT is a short term for distributed hash table, and is a set of protocol used on the IPFS network to share a table which says to this key, that means distributed key value storage, completely decentralized. Now, who is familiar with the Kademlia, or CAD for short, DHT? Anybody? Okay, I was not expecting anything else, honestly. Absolutely, don't worry. Now, IPFS uses the Kademlia DHT for keeping the peers and blocks availability. In short, when you search a file on IPFS, you first say, I want this CID, right? Okay, let's look at my neighbors if anybody has this CID, and eventually this neighbor will search on another neighbor and so forth. At some point you say, okay, this peer has this CID, right? This host. Okay, fine, but of this host I don't have the IP, I have the peer ID, which is basically a unique ID for each host in the network. Then you have to make a second search saying, please somebody can tell me which is the IP of this peer ID. So there are two searches that have to be made. Unfortunately, Kademlia DHT uses a protocol called Gossip Sub for keeping this kind of information, which is a protocol that relies on long-living connection to your neighbors and maintaining a list of connected hosts and so forth. If you remember what I talked about at the beginning, this was the reason why new hosts could not be added in the original system, because it takes a lot of time to be effective in the Kademlia network, up to 2 days, in order to bootstrap. Moreover, our Elastic IPFS system, even though it's an AWS cluster, to the outside world is seen as a single node, and it only exposes a single peer ID. This has a problem. Since we are on the cloud, we cannot really maintain outbound long-living connection, and therefore eIPFS was not able to directly participate in the DHT network for basically publishing and advertising content. Therefore, it was not self-sufficient, and it needed help from auxiliary system made it for the exact scope. And then it comes where the Protocol Labs people, the company that we worked for and with, basically helped us on this thing. First of all, they created the Hydra nodes. The Hydra nodes is a very, very nice piece of architecture in this software, not because of the technical complexity of the component itself, but for the idea, because they really used a very nice idea in order to basically to help people search for stuff. How they work? Basically, the Hydra nodes are created in a way that there is, when you search for something in the DHT network, there is a very, very high probability that you will reach one of the Hydra nodes. The Hydra nodes are basically very, very powerful because they all shared a single data storage for reading the current value of a key in the DHT. So if a node, let's say in São Paulo, gets the information about a value, that value will be, that key, a key will be immediately available to all the nodes in the system for the next search. So if somebody else in Japan 1 minute later search for the same key, will immediately get the key value. So they are very powerful on this. Now, additionally to this, the reason why are so the reason why they are successful because the Hydra nodes are designed in order to be geographically to be your neighbors, but not geographically, but to the DHT sense. The reason why I'm saying that is that when I say your neighbors, on the DHT does not mean that I am your neighbors if I'm physically close to you. I am your neighbor if the modulo operation on my peer ID gives the same result as yours. There are basically 2056 available buckets. I will fit in one of those buckets according to my peer ID. And then is where the Hydra node shine, because basically when we generate the peer ID for an Hydra node, we make sure that there is an Hydra node in each bucket in the DHT. So everybody has a Hydra neighbor at any time, or multiple Hydra neighbors. And that's where the Hydra nodes are very, very successful. The second system that was needed in order to make this thing work was the indexer node system, which is another system that basically exposes an API to other provider to send data and say, look, I have this data, please advertise this data for me. And the indexer node provides an HTTP API for other peers in the network to query via HTTP rather than the DHT. So basically, when you advertise to the indexer node, look, I have this data, immediately after, if somebody asks for data, is able via HTTP, it immediately gets a reply, which is a positive or negative reply, without all the delegated search that is in the DHT network, which is usually what is messing up and making everything slower. The indexer node exposed two API for this purpose, for feeding data to the indexer node. One is the HTTP API, and is the gossip sub. Of course, you already know that we are going to use the HTTP API because I already told you that we cannot use gossip sub. Why? Because we are on the clouds. Once again, we cannot maintain long living connection, and it's very expensive. Gossip sub, even though we cannot, let's say we find a way to maintain a long living connection, right? The problem is that gossip sub is very verbose. We're going to receive information about other people in the network that we don't care about, and unfortunately, this impacts the cost because there will be the network ingress and egress transfer, so we have to make that slow. Also, we run in one optimization of libp2p, which is the internal network stack used by IPFS, that nobody usually has faced yet because it was a very unique scenario, which is if you think about a very clever optimization that in our case was also eating and making the problem very, very hard for us. And that's the following. As I told you, we use Lambda to publish, right? So if it very easily happens that two Lambdas exposing the same peer ID might want to participate in the DHT at the same time. This basically leads to the fact that there is a high chance that two Lambda will connect to the same destination at the same time from two different locations advertising the same peer ID and start sending some data. Now, on the receiving side, the host will see two connections from different sources, and it will assume that one of the connection is old and stale, and the host is connected to a second location, let's say a mobile network switch or something like that, and it will just kill the first connection and try to migrate all the communication on the second one. On an average use case, this is a very clever optimization in order to maintain connection even if you switch protocols, right? In this case, it was eating we were eating our toes because we were basically get the connection interrupted, so we could not use this kind of connection at all. Now, how does the HTTP ingestion works? it's pretty easy. The thing is that it's not a pushing API, but it's a polling API. So basically, the indexer node basically wants us to upload new data, or actually make some data available on HTTP somewhere. Usually, is an HTTP stored somewhere else. And then, when we are ready and we update the head URL of the queue, we notify the indexer node on the /ingest/announce endpoint, which basically tells the indexer, look, the head of my queue has changed. When you're ready, download it. You have to think about, when I say about the head of the queue, I'm talking about a strict queue with a previous link, because they implemented the indexer node in a blockchain fashion. So basically, you download the queue, and I mean, as I've seen here, when it's ready, the indexer node will download the new head of the queue, read the information, then follow the previous link, download the previous link, and so forth. And it will repeat this flow until it reaches an advertisement that it has already reached, or it will reach the tail of the chain, which basically in the very beginning there is no previous link. This is a very nice architecture because in theory, if you now start a networks indexer today and you start hitting one server, you can immediately download the head of the queue back to the tail. In the effective world, this doesn't happen, because if you follow that you already have millions of uploads per day, you know that you're never going to finish. In theory, you might finish at some point. You can try if you want to. There is a public network index. If you want to download the queue, just go. Now, let me briefly introduce the 3 files that are needed from Elastic IPFS to make it downloadable from the network indexer. The first one is the head of the queue. On line 3 here, basically, you see that there is a link to a URL that you need to download, which is a link to the head advertisement file. The advertisement file is very simple, because here you have the address of the peer ID that you want to, where you can download, the address of the location that contains the entries. Here you have the context, which is basically just sample data that you don't care about, and these are the entries, which is the file that contains the list of content that I'm actually publishing to the DHT basically. And finally, here in the provider is the peer ID that actually is publishing this content. Finally, the previous ID, as I told you, is a link to the previous advertisement. Finally, there is the entries file, which only contains a list of CID that we are publishing, whereas this one is very, very trivial. Basically, there's nothing else to really say. Finally, we get back to the original route, which is the publishing subsystem. The reason why I explain how the DHT works is to let you understand why the publishing subsystem is made this way. Now, publishing subsystem is pretty simple. Once again, don't try to read this graph. At the end of the day, SQS to Lambda, SQS to Lambda again. Now, you might figure why you're doing SQS to Lambda twice. There is actually a reason. The concurrency problem, because handling the huge load without losing any data was a big mess, because several millions of blocks per day were uploaded every day, so the queue might easily explode. And actually, when I say millions there, I'm actually underestimating the problem, because as I told you, there is no clear relationship between the number of car files and the number of blocks. Moreover, no advertisement could be lost, because if you lose an advertisement in the middle of the queue and you don't publish, the indexer will never fetch it, and it will never be added to the DHT, which means that all the entries that were contained in that advertisement will never be available on the DHT at all, which is, of course, a huge mess. Moreover, this also led to another problem. Another concurrency problem was if we start, let's say a Lambda, say I take the advertisement and update the queue. I take the advertisement and I update the queue, right? If we have a concurrency problem, we easily see a race condition problem here, because if two lambdas are trying to update the queue the head of the queue at the same time, one of them will kill the other one, and the entire chain on that stuff will be lost, and you cannot do that. What do we do? We're stuck? Well, no, don't panic, we're not. Basically, we split the publishing flow in 2 steps. That's why I repeated myself, SQS lambda, SQS lambda. Because basically what we did was that we grouped in the first step, we grouped the entries in a basically a list of entries file and an advertisement. That operation can be done at any concurrency because we don't care about the sorting order, there's no problem in that. And an advertisement file is made. Then we basically create the advertisement and we publish them to the S3 bucket, destination S3 bucket, and we also update the head of the queue with the concurrency set to 1. Now, the thing is that each advertisement file contains 10,000 entries, which means that if we are able to create with concurrency 1 an advertisement file, we can probably publish a lot, right? How much is a lot? If you carefully think about that, if you take as a target number of blocks per day that you want to publish, the 1 billion, right? And you say, okay, I can group them in advertisement on 10,000, right? So you end up having 100,000 advertisement that you need to publish in a day. And if you make that divide by the number of seconds in a day, you just realize that you have just to publish 1 advertisement per second, which is way more than you can do way better than that, right? But even this case, which is pretty good, it only requires 1 execution of that lambda per second. Given that lambda usually executes in few milliseconds, you can do probably several billions per day, which basically means that setting the concurrency of the publishing lambda to 1 was absolutely fine. And in fact, we were able to advertise 1 billion blocks per day without a breeze, basically. So basically, the flow was basically SQS topic. We execute the lambda once. We execute another SQS topic. We execute the second lambda. All these lambda produce a file which is stored on a dedicated S3 bucket. That S3 bucket that has only public data, so it's completely public, is directly served over the network indexer via HTTP. Fun fact, in that case, we are leveraging S3 capabilities, so we are not spawning a separate HTTP server for serving S3 content, but we are directly serving the S3 as a bucket. Basically, we are leveraging the hosting solution by AWS in this case. Finally, there is the third and last subsystem, which we call the peer subsystem. This peer subsystem is, once again, this is the overview, is a completely automatic, stateless, and lean EKS cluster. So it's based on Kubernetes, are a bunch of auto-scaling Node.js nodes that can serve the data via bit-swap protocol. And that leads to a very important choice that we made in order to have this solution possible and available. We needed to simplify the bit-swap protocol. The bit-swap protocol, which is used by the IPFS implementation, was not stateless because you were supposed to do the ledger manager, the want list manage, fetch data on behalf of people that asked you, and so forth. So basically, the idea behind this is that I connect to a peer. I say I want this list of CID. For the one that you already have, that you start sending immediately. For the other one, remember that I want them if you eventually incur into them, or you want to fetch them for me, and then later you can send them. So you have to manage the list of CID that a specific host wanted. In this case, since we wanted to be stateless, we could not do that. So we removed from the bswap. So we made some assumptions saying we never fetch external data. We only serve data that we have at that moment, and that's it. That's how bitswap became, first of all, stateless, second of all, read-only on Dynamo, and basically able to scale at any time. The general idea on the peer subsystem characteristic was that when you connect to me and say, I want this CID, I immediately read from the blocks table in Dynamo. If I found an occurrence, I make as S3 request, and I serve directly the file to you in memory without storing on the host in the middle. I just basically forward the stream in Node.js. And moreover, I leverage the property of the car file because I only do the random access in the car file very quickly using HTTP byte range request. Now, I think I killed you enough with all these concepts and techniques and protocols and so forth. So let's get to the results, right? How does eIPFS perform? This graph shows the hit rate for 200 terabytes of data. Now, I challenge you to spot when in this graph eIPFS was actually deployed. And of course, is here. We went from a rate of 5% to a rate close to 100% steadily, because basically since here we were steadily between 100 and 95% all of a sudden. But even more, the average indexing time has dropped. This graph is not cut at the end. The problem is that here is when the Elastic IPFS was deployed here, and basically the average indexing time went from 3 minutes to few milliseconds. So we gained several order of magnitudes in performance. And finally, these are the numbers. After 6 months in production, we got 180 million car files uploaded, which makes us on average 1 million per day. We indexed 16 billion blocks steadily, and there is a relationship of 24 billion blocks to cars relationship. The reason why these two numbers, the 16 and 24 millions, apparently don't match is because the idempotence was removed lately in production. So initially it was using the idempotence, which was not using this technique. That's why we have far less links that we should have actually. There are legacy tables that will still have to migrate. But once again, we are handling without any problem, and with the performance that I showed you before, 180 million cars in just 6 months in production, and with a single deployment of Elastic IPFS. So we are talking about auto-scaling lambdas and an auto-scaling EKS. That's it. That's pretty much it. Now, what we can learn about this long journey? First of all, let me go to the less important. First of all, HTTP is not dead yet, at all. People start writing very nice protocol or doing a lot of fancy stuff over just TCP, UDP, whatever, a lot of stuff. HTTP is always there to save your projects because it's very reliable, very performant, and if you use the entire HTTP, then you can be very, very performant. To give you an idea, I was able to, on one test, to outperform local file system reading in EC2. Instead of using local Go implementation and reading local with EC2 on local file system, I was instead saying I'm going stateless and I'm reading from S3, but I'm leveraging HTTP pipelining. I was faster than the Go implementation, which was just reading locally. So you just have to know what you're doing. In that case, HTTP might be very performant. Disclaimer, I work on the HTTP team at Node Core, so I'm a little biased, but that's another thing. Forget about it. Another thing, democracy is very good. What I was saying, if you remember earlier, I said that we are not logged in AWS, and AWS was just a reference implementation. One thing that I forgot to mention is that, purposely forgot to mention, is that another benefit of not having vendor lock-in is that you cannot use very fancy specific tool that the cloud provider is offering you that most of the time works, but they force you in a very horrible pattern, which later in the project, if it becomes too complex, they might eat you back. Considering that this was just a reference implementation that was supposed to be translatable at any time to another cloud provider, we chose basically to stay on a generic pattern with very generic components. Like I said, You could swap Dynamo with Redis and nothing would happen, right? And that was good because we basically helped out to stay simple, very, very simple. Lately, if you remember, I started my presentation saying that in life all you need to be successful is love, right? That's why you need the KISS rule over there. That's it. Do you know what KISS in that stands for there? Does anybody know? No? Yep. Keep it simple, stupid. Which means that IPFS protocols can be overly complicated. There are a lot of aspects. You have really no idea how many abstracts are out there for IPFS. The only way that you have to be successful in building this kind of architecture products very quickly and in a reliable way is simplify. If you have a protocol that have 25,000 rules, you probably just need 100. Just implement those 100. If your product is viable, forget about everything else. Keep it simple. Just implement the bare minimum that you need in order to be successful. And eventually, later, you can add things back. But at the beginning, stay simple. If I was trying to implement the entire Bitswap protocol, I would never be successful because it was very complex. So I say, you know what, I don't need this thing. Let's deliver what I actually need. One last thing before we part. Keep your eyes on the stars and your feet on the ground. What I mean by this, you have a very nice implementation, you have a lot of stuff you want to do, you can do everything, we can heavily over-engineer stuff very easily, but we have to deliver to people. There are, all of us have significant others which are not technical and don't give a shit about how we design these protocols, right? Stay simple and try to feed those people. That's it. So remember that we are not doing this thing mostly for ourselves, but even for end users, and they won't have easy to use tools and they don't care about the technical complexity or the technical beauty, provided that they might understand why some technology is beautiful and sometimes some technology is horrible. That's pretty much it. Final quick citation of my company, Nearform, that has sent me and my colleague Michele here. We are a global consultancy company, which more than 300 people and counting. We are very present on NPM. We have a monthly downloads of 1 billion packages on NPM steadily per year. If you are on if you use packages, probably you run our packages. I'm sorry, there is no escape. That said, we are a very wonderful company. If you want to know us or get to work with us or hire us, you can reach out to me or my colleagues Michael after this talk.